Hello, I'm Berenice.
And hi, I'm Vishwajit, and today we'll be explaining what we did for our 2023 summer research project. And the title of our project is Identifying T Brown Dwarfs and Measuring Their Velocities.
So first, I'll explain what a brown dwarf is. A brown dwarf is an astronomical object that falls in between a planet and a star. They are too massive to be considered a planet, but not massive enough to produce the heat and pressure required for hydrogen fusion, which is the requirement to be a main sequence star. Although brown dwarfs can't fuse hydrogen, they can fuse deuterium, which is a hydrogen atom with a neutron, and brown dwarfs more massive than 65 Jupiters can also fuse lithium. Brown dwarfs form via the collapse of a gas cloud, like a star, rather than accretion around a star, like a planet, hence why they are referred to as failed stars. Some of the smallest brown dwarfs can be confused with large gas giant planets, and in terms of mass and brightness, they can be indistinguishable.
A brown dwarf spectral class is based on its surface temperature. Its transition to different spectral type as it cools down over time. As this diagram shows, M dwarf are the warmest and often youngest, and Y the coolest and older brown dwarfs. With this, we have a comparison with a gas giant planet. However, gas giant forms in protoplanetary disk, which reflects light and lack a spectral classification. While the brown dwarfs cool over time, gas giants are a part of a planetary system. In the paper shows the evolutionary tracks for a low-mass stars, brown dwarf, and a planetary mass objects. It illustrates the relationship between the effective temperature, which is T effective as shown here in Kelvin, and the spectral type of this object as they age over years. The line in the figures represent the individual objects and they are color-coded according to their initial mass. This figure was adapted from a study by Burrows et al. In 1997. The figure also provides a visual representation of how the effective temperature and spectral type of low-mass stars, brown dwarf, and planetary mass objects change over time. It helps in understanding the evolution of these objects and how their properties vary as they age. Now, here's an Hertzsprung-Russell diagram, which is utilized to understand the relationship between the luminosity, temperature, and spectral characteristics of star. It helps astronomers to classify stars based on their evolutionary stage and aids in identifying patterns among different types of stars. Specifically, for brown dwarfs, the HR diagram is valuable in placing them accurately. Brown dwarfs, the smallest and the coolest star, reside at the lowest part of the main sequence on the HR diagram. Despite being at this location, they are not considered as the main sequence stars because they do not undergo hydrogen fusion. Brown dwarfs labeled as spectral classes L and T are plotted on the HR diagram according to their parameters, while some brown dwarfs can fuse deuterium if they achieve a core temperature of 1 million degrees. Those that are too small for this process are often referred as an orphan planets. Thus, the HR diagram helps us in classifying and understanding the unique characteristic of this brown dwarfs within the broader context of a stellar evolution. Go on.
The purpose of this project was to identify new T-type brown dwarfs and measure their proper motion and tangential velocity. We targeted T dwarfs specifically because L dwarfs, the warmer type, can be a mix of young brown dwarfs, but also older low-mass stars. Y dwarfs are too dark and cool for the scope of this project. Hence, focusing on T dwarfs ensures that we are looking at brown dwarf objects. In addition to this, since T dwarfs are faint, the ones we detect would be nearby. This is why we measured their proper motions. A high proper motion indicates the object close by. Thus, a faint object combined with a high proper motion indicates that it is intrinsically faint. This is how we will know for certain if our targets are brown dwarfs. By discovering new brown dwarfs, we contribute more candidates for further study in future projects.
Let's start by talking about the formation of this T brown dwarf. Like other brown dwarf, T-type brown dwarfs form from the gravitational collapse of gas and dust clouds, but they do not have enough mass to ignite as stars. T-type brown dwarfs are a classification within the brown dwarf category, characterized by their spectral signature in the infrared part of the electromagnetic spectrum. T-type brown dwarfs have relatively low surface temperature compared to the stars. Their temperatures is typically a range of between 500 to 1400 Kelvin. What sets T-type brown dwarf apart is the dominance of methane in their atmosphere. Methane absorbs and emits light in the infrared, which makes them detectable in the part of the spectrum. Some T-type brown dwarfs exhibit variability in their brightness, which can be caused due to the atmospheric changes, rotation, or other factors. Because they emit most of their light in the infrared, observing a T-type brown dwarf typically requires a specialized telescopes and instrument designed to detect infrared radiation. Now here's a picture which was taken by a near-infrared observatory, which is Gemini North, and that have detected ammonia in the spectra of the coolest brown dwarf ever discovered, which is as shown in the figure, which has a temperature of roughly 350 degrees Celsius and a mass between 15 to 30 times that of a Jupiter. This is the first time such a finding has been made in a near-infrared spectra of a substellar object other than a planet. Ammonia is a key identifier in classifying this object in the middle ground between a star and a planet. Until now, only planets have shown ammonia signatures in their near-infrared spectra.
Professor David Pinfield is a researcher and lecturer in astronomy at the University of Hertfordshire and was our supervisor for this project. Professor Pinfield had prepared an Excel spreadsheet of targets with coordinates, magnitude, and colours. The following is an explanation of how he obtained these targets.
Sources were downloaded from the Vista Science Archive, which provides images in J, K, and some H magnitude. T-dwarf have a blue infrared color, so to select objects with T-dwarf trait, the J magnitude had to be greater than 12. And the sources either had non-detection in K and H or to have colors of this criteria, which is given on the screen. Presented here are the filters utilized in our project, each specified with its corresponding wavelength. Our study involves service, namely DES, Vesta, which will be elaborated on a subsequent slide. Given the inherent faintness of T-dwarf, our observations span the visible region in optical to infrared and far infrared. This approach enables astronomers to peer into the space regions which is obscured by a cosmic dust, revealing the insights that is not accessible through visible light alone. Now, this Vista sample was then cross-matched with the dark energy survey using a 6 arcsecond cross-match radius. And this color, as you can see on the screen, were calculated and the conditions were further reduced the initial sample. Finally, the remaining sample was then cross-matched with a WISE catalog, which is a WISE survey, and anything with this color range were rejected. This process resulted in the identification of 344 potential T-type brown dwarf candidates for further analysis. Data sources include Vista, DES, and WISE.
Despite the aforementioned, the images still require a quality check to ensure that an object was indeed present in each image. Each target had RA and DEC coordinates and values for apparent magnitude of several different photometric bands. So first, images in the J band were downloaded from the Vista Science Archive to check that there was a point source object located at the correct set of coordinates. The picture to the left shows an example of one of our targets being clearly visible as a point source at the center of the image. If a point source object was not visible at the right coordinates, the image was corrupted, that target was discarded. So here on the right, we have some examples of images that could not be used. On the top are two examples of images that are too corrupted to be usable in any capacity. Whilst on the bottom, we have bright objects providing noise. And as a result, we cannot tell which of these white pixels are noise or a star and are thus unusable. Next, single images and stacked images from the dark energy survey in the G, R, I, Z, and Y bands downloaded from Astro Data Lab. The brown dwarf object is expected to be visible in Z and Y, which corresponds to the infrared wavelengths. They're very faint or not visible in I, which corresponds to near infrared, and not at all visible in G and R, which correspond to green and red visible wavelengths. If an object was still visible in G and R, it's more likely to be a star and would be discarded. So these 5 examples here show one example of what we expect to see. So in Z and Y, we can clearly see that in the center of the image that there is a faint but clearly defined and visible point source. Whilst in I, it is extremely faint and you can barely see it. Whilst in G and R, you cannot see it at all. If it was visible in G and R, it would most likely be a star and not a brown dwarf. It would be too bright. Finally, the target was checked in the Infrared Science Archive, where we looked specifically at images taken by WISE, the Wide Infrared Survey Explorer. WIDE is a space telescope that conducted an all-sky survey in 4 different wavelength bands in the infrared. For brown dwarfs, we focused on images taken in the W1 and W2 bands, which correspond to 3.4 and 4.6 microns respectively. A brown dwarf should be visible in W2, but faint or absent in W1. So in this example on the right is the W2 image, and as you can see under the yellow cursor, there's a grey blob. That's our target. But on the left in the W1 band at the same location, there's nothing there. If there was an object visible in W1, then that object would be discarded, as it would most likely be, again, a star, not a brown dwarf. Going through images from those 3 databases reduced our initial sample size of 344 to just 48 candidates.
Having filtered out with all our samples using the aforementioned survey, the next step involved verifying whether each target was indeed a brown dwarf. This verification was accomplished by calculating the proper motion, which is a critical metric in understanding an object motion in the sky over time. Proper motion is particularly useful in distinguishing between distant background stars and nearby celestial objects. To determine the proper motion of our target, we measured their coordinates at 2 distant states and computed the velocity based on the difference in the coordinates and dates. The importance of proper motions lies in the ability to discern the true motion of an object against the backdrop of a fixed stars. In the provided figure, the left image contrasts the right, both captured at different epochs. Notably, the objects of interest is centrally positioned, as you can see here. And getting all these values, which is the RA deck, the position, and the date of 2 pictures when this was taken, plugging the values into the equation, we find the proper motion, total proper motion in arc seconds per year. Now, next, we'll be looking into a blink comparison, which was conducted using these 2 images. This animated slide visually demonstrates The shift emphasizing the movement of our subject, which is a brown dwarf, in relation to its background standard stars. This process serves as a conclusive confirmation of the object classification as a brown dwarf.
Using color diagrams we sourced from several different papers, references will be given on screen. We estimated the spectral type for each target. So here we have a diagram for the color Y minus J. As you can see within the diagram itself, an example is given for Y minus J equal 2.3. As demonstrated here, you'd go along the XY axes to find your value for color and go across the x-axis until you hit the first data point, which should be your warmest possible spectral type, in this case L2. And you would continue until there is no longer any contact with the trend, in this case all the way to T9. We then go to another color diagram for a different color and repeat the process. In this example, for J minus W2, we can see that there is a dip here, which results in two possible spectral ranges. The trend looks different. We would then estimate the spectral range for 7 different colors for each of our targets. And we then determine what is the most likely spectral range based on which spectral types are most common across the different colors. The absolute magnitude for the spectral types were estimated using values provided by a paper, title on screen. Since spectral types have a range, a minimum and maximum absolute magnitude was given to each target. The distance modulus and then distance in parsecs was calculated for each target. Each target ended up having 2 different values for distance.
The next crucial step was figuring out the tangential velocity, which is a method that helps us to understand where the brown dwarfs are originated. By calculating the tangential velocity, we could estimate the birthplace of each object. Typically, a brown dwarfs originate from the thin and thick disk of the galaxy. If a brown dwarf came from a galactic halo, that would be an unusual and require more investigation. To help this visualize, let us consider a simple figure which illustrates the peculiar velocity of the Sun around the galactic center at a distance of r0. Another part of this figure shows the velocity component, which is v, r, v, theta, and z, is in cylindrical coordinate system, telling us about the different velocities which is experienced by the star. And we have this black arrows which indicates the direction of the galaxy rotation. Now, keeping this in mind, we then have the equation for our tangential velocity as given here, which converts the parsecs per year to kilometer per second as shown. And a table displays the estimated tangential velocity of some of our targets. Most brown dwarfs, as expected, came from the thin and thick disk, while a few had a velocity suggesting that they might have originated from the galactic halo. Given the range in our spectral types, we obtain the 2 distance values for most objects that leads to an identification of some of our targets likely coming from a different regions, adding an intriguing layer to our findings. We then identified a total of 33 brown dwarf objects in our study. To ensure the novelty of our findings, we cross-referenced this import coordinates of this brown dwarf with the Simbath database. Surprisingly, 14 of our objects were previously undetected, marking them as a newly discovered celestial T-type brown dwarf. In assessing their characteristics, particularly their colors, we estimate the probable range of their spectral types. And as we can see over here, based on our spectral type, in few of our objects, there is no result, which means there was no survey conducted using the WISE telescope for this given target. Notably, all our objects were likely to be T-dwarfs, a classification indicative of their cool and faint nature.
If we were to do another study on these objects that we discovered, we would want to observe these objects directly and obtain more accurate measurements for proper motion, color, magnitude, and perhaps other parameters. These brown dwarfs could also potentially be searched for exoplanets. So here on this screen are the references we used for this project. You may pause the video and search them up in your own time. That's all we have for today. Thank you so much for watching our presentation. We hope you learned something new. Please feel free to leave a comment or ask any questions.
Thank you.
Thanks.